disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media accounts to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media accounts to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this.
How much time you will
How?
take to go home?
Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media accounts to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social media accounts to spread facts and solidarity. This will help us to prevent the spread of COVID-19. Hi, my name is Cassie, and I'm 16 years old. I've seen on social media that the new coronavirus outbreak has provoked a lot of social stigma and discrimination. This is harmful to not only those who suffer from it, but for everyone. Stigma can isolate people. It can drive people to hide their illness to avoid discrimination, and can even prevent them from seeking medical care. So it is very important to avoid stigmatizing people. And we can all do this. How? Basically, by understanding that words matter. Do talk about the new coronavirus, but don't attach locations or ethnicity to the disease. Do talk about people who have or may have COVID-19, people who died after contracting COVID-19, but don't refer to the people with the disease as COVID-19 cases or victims. Do talk about people acquiring or contracting COVID-19, but don't talk about people transmitting COVID-19, infecting others, or spreading the virus, as it implies intentional transmission and assigns blame. Do speak and share accurate information about risk from COVID-19, but don't repeat or share rumors that are not confirmed or language that spreads fear. Do talk positively and emphasize the effectiveness of preventative measures, such as hand washing, but don't emphasize or dwell on the negative or threatening messages. Most importantly, do good. Use your social.
Hi, good afternoon to you all. Today we will be discussing about the subsidence, its prediction and control in mining. After this lecture you will be able to understand what is subsidence and under what circumstances it is occurring, and how to control the subsidence. And one important outcome of this lecture will be that you will be able to at least predict what is the extent of subsidence in a mining area. With this with this knowledge you will be at least getting rid of the consultants who are doing the prediction of subsidence in the mining area. So you yourself will be able to calculate the extent of subsidence in a given mining scenario. So once you cover this lecture and go out of the college in the field, you need not depend upon the consultants. You can yourself find out the subsidence in the mining field. For the especially for the coal, I'll be discussing you especially for the coal, where lot of subsidence issues are there. For metal as such, big issues are not there and the calculations are complex, so that we are not going to deal. But once you understand the algorithm for this coal mining sector, you can very well extend it to the metal mining sector after few study of the research papers. Okay, are you all able to hear my voice? Is the voice quality okay? Okay. Okay, then let us start with the basics of subsidence. Mining induced subsidence. Okay, surface subsidence is nothing but its lowering of the ground surface following underground extraction of an ore body. Right, so whenever you do mining, a void is created underground, and this void tries to fill up by the breaking of the roof rock, and it tries to fill up that space, and in this process the cracks in the roof, they get extended up to the surface, which lowers its elevation. So that causes subsidence. So subsidence can be divided into two parts. One is the continuous subsidence, and another is the discontinuous subsidence. Okay. Continuous subsidence occurs mostly in flat deposits. Okay, and the displacements are very less, sometimes in the elastic order of magnitude. Elastic order of magnitude means the subsidence up to the surface is showing a depression, but it is not breaking onto the surface, whereas in the underground it may have broken. Okay, and it's mostly associated with the extraction of thin horizontal or flat dipping ore bodies, which are overlain by weak or brittle sedimentary strata. On the other hand, discontinuous subsidence is a change in the uh, uh, it is characterized by large surface displacements over limited surface area and the formation of steps or discontinuities in the surface profile. And these kind of discontinuous subsidence, they occur mainly in uh, metalliferous mining deposits, where the deposits are almost vertical or subvertical. So some of the examples of discontinuous subsidence is the crown hole subsidence. Okay, it arises from the collapse of roofs of generally abandoned workings. If you have a working in an inclined deposit, and this working, say, it has been abandoned for a quite long period of time, then over a period of time all these strata, they progressively fail, and they try to create depression on the ground surface. Sometimes this cannot reach to the surface, so there in some cases it doesn't create any subsidence issues. Okay, so these look like something like this kind of subsidence are known as crown hole subsidence. Another kind of discontinuous subsidence is the chimney caving or piping or funneling. They can be termed through these three words. Okay, here also, as the mining is carried out in this area, the surface subsidence takes place, and because of this weak strata, there is a depression on the ground surface. Okay, this mainly occurs in weak overburden materials and in previously caved material, and mostly wherever you find there are jointed rocks, there they occur. Okay, and in some cases it has been found to propagate up to several hundreds of meters. Okay, another kind of chimney subsidence, also known as the plug subsidence. What happens is that you have a mining deposit, you are mining at the bottom, okay, and certain portion of the strata is engulfed between two cross dikes. Now, the moment you release the material from the bottom, this complete thing can shift up to the uh, excavated area, and this can come down just like a plug. Okay, so this type of subsidence is known as the plug subsidence, and one typical example is from Athens mine in northern Michigan, where the cave was developed and rapidly it progressed to surface through 600 meter of cover. Okay, so these are some of the monitoring dates what they have done. In 1932 this has caved, this plug caving occurred, and later on people had started monitoring. So after this dike issue there was no such subsidence there. Okay, so this can happen typically when you get dikes in the metalliferous deposits. Okay, Srimaya is asking, please repeat again the crown subsidence. Okay, and another question is, any such example in India with respect to plug subsidence? No, as such, with respect to plug subsidence, nothing has been observed. And crown subsidence, let me tell you. This is generally happening because the workings are failing. When you have created a void in the workings, this void has to be filled up. Okay, this void tries to be filled up with the breakage of the strata above it. If the strata is very weak above this working, and other areas if it is strong, then in that case this weak portion will start collapsing and filling into the ground, and then this depression continues and extends up to the surface. These type of things are known as subsidence, are known as crown hole subsidence. Okay. One example is from Colebrook North Colliery in South Africa, where a room and pillar mining covering approximately 3 square kilometers suddenly collapsed with loss of 437 people. Okay, and these can also be treated as a special case of chimney caving, because a certain weak zone of strata is there. And in Indian cases, in coal mines, you get few crown hole type of subsidence, which are termed as pothole subsidence in Indian scenario. Okay, some 30 to 40 mines at shallow depth, these have been reported in India also. Okay. So when this thing was plug subsidence and this crown pillar subsidence or chimney caving subsidence are being studied, a lot of research was carried out in 94 by Bitoni, and he reported the analysis between the stope span. The width of stope span is the width of the stope, which is denoted by L. Okay, rock mass cohesion and factor of safety. How much factor of safety has to be maintained? So they came out with a guideline that what should be the best span of the stope for a given factor of safety. Say for example, your rock mass cohesion is 0.14 MPa, okay, and you want to make a factor of safety against chimney caving as 1.5. So from 1.5 you draw a horizontal line going up to cm, and from there you drop a vertical line, so it comes out to be 10 meters. So a stope span of 10 meter width will be sufficient to prevent chimney caving against a factor of safety of 1.5. Okay, but then this relation has been developed for that another country, and that was for Michigan. Okay, so for Indian condition these things need to be developed. So far there is no guideline, but that can be tried, and to some extent it can work in Indian conditions also. Okay, but a lot of research is required to develop this kind of curve. Okay, another kind of subsidence you see is the sinkholes. Okay, sinkholes are basically the cavities which are known as solution cavities in limestone deposits. Because of acidic water, this limestone gets dissolved and they try to form cavities. Okay, so you may have a deposit, sometimes it will be covered with alluvium, but in the underground or in between this strata you will find there are cavities, and this can break any time. Okay, one such big disaster that occurred in Dolomite sinkhole was in West Rand gold mining district in South Africa. Okay, they were trying to build a 3-story crusher chamber over the deposit, and suddenly the crusher chamber fell into the cavity, claiming 32 lives. This happened in 1932. So whenever you are working on dolomite deposits or limestone deposits, it's always better to investigate any presence of any cavity below the ground. Okay, this can be investigated through ground penetrating radars also. Lot of techniques or geophysical techniques are there. With this it can be investigated. Okay, so sinkholes have these kind of issues. Okay, sometimes they are also known as karst, when large volume of rocks are dissolved. Okay, they are also known as karst features. Another example of discontinuous subsidence is the caving, block caving. Okay, so when the rock is very weak and fractured, the mining is started by creating wide entries, and because of these wide entries automatically the material starts flowing out, and then the materials are taken out through the stopes. Okay, so block caving has its own mining layout that I am not discussing, but general look of this block caving can be seen like something like this. So once this material, this fractured materials are taken out, that is the mineral, there will be a caving on the ground surface. Now here it is shown as a vertical deposit, it can be inclined also, so there the subsidence will be quite different. And mostly in metal mines what people prefer is that they don't allow any habitation near the mineral body. because the subsidence is unpredictable there. Okay, as far as mechanics of the subsidence is concerned, this suppose the material has been extracted from the extraction level, the material caves down, then there will be some uh, fractures that may be occurring. Okay, and one important terminology with respect to subsidence is from the bottom of the seam up to the surface. If you draw a straight line, and so its inclination with respect to the horizontal is known as the angle of break, and with respect to the vertical is known as the angle of draw. Okay, that means complement of the angle of break is also the angle of draw. Sometimes even after the subsidence there will be progressive failure of the hanging wall, because this wall becomes vertical, suppose, then in that case, if all this material are withdrawn, this wall will be left free, and vertical walls normally try to tend to show a failure. Okay, so these there apart from subsidence there can be progressive failure of the hanging wall also. Now coming to the subsidence in coal mines. Coal mines are facing a lot of subsidence issues, especially in Jharia. You must be reading in the local newspaper that Gof has subsided and the gas came out and the complete hut has gone into the ground. Okay, so those issues they occur mostly in coal mines. So suppose you have a coal seam. Okay, this black one is the coal seam, and if you extract the mineral from here, the extent of subsidence will be dictated by the angle of draw. Okay, this J, and the extent goes to the surface with this angle in all the directions. Okay, so this angle of draw is one important parameter that is used to define what is the extent up to which the subsidence will occur. If W is the width of the area, then the subsidence will be W plus twice the height into tan of angle J. Okay, so this much it will go. Now you go on increase, if you suppose you go on increasing the width of the extraction, then this subsidence will also go on increasing. Okay, we will come to the point what is critical, subcritical subsidence. Okay, so this way this subsidence profile is created on the surface because of removal of this much area. Okay, and the maximum depression is denoted by capital S, and half of the subsidence, half of the total of maximum subsidence is S by 2. Okay, this is a point where this which is of interest for many subsidence engineers, because the slope of the ground changes from convex to convex in this area. So it will be convex in the from the edge to half of the subsidence magnitude, and beyond half of the subsidence magnitude up to the full subsidence magnitude there will be concave area. Lot of chats are coming up. Sir, there must always be some error associated with finding the point of zero subsidence. How it is taken care of? Okay. See, the zero subsidence is taken care of by this angle, and this angle of draw actually is a field dependent criteria. Okay, so lot of say mining it has been done, and lot of studies on subsidence has been carried out. So people try to fit a plan over, suppose you fit the plan of the mining area over this surface datum. Okay, so at this point you got the you say that you have started the mining and the subsidence has extended up to this point. Okay, you know the depth of working, you know the width up to which it has extended. From that the value of xi is calculated, that is the angle of draw. Okay, so it's a field dependent parameter, and after taking average of 5 to 10 values of the angle of draw in the field, you get the value of xi, and with this you can this parameter can be used further to predict the subsidence. That I'll be coming to that point after some time within this lecture. Okay, so this is the curve of the depression, and if the slope of the subsidence profile is plotted, from here it starts from 0, slowly it increases, and at the point of half of the subsidence it starts decreasing. So this point, half of the subsidence, is known as the inflection point in subsidence profile. So that's why this S point S, where small s is equal to capital S by 2, is of greater interest for the subsidence engineers. And then the slope of the ground starts reducing, and at the point where there is maximum subsidence, the slope of this curve is horizontal, so it is 0, and this part again becomes symmetric with the left part, provided the seam is horizontal. Here it has been shown to be inclined, so this right part will not be symmetric. In fact, this right side there will be more of the extent of subsidence will be more. Okay, another curve that shows the most of the information related to this okay, there are no chats. Okay, see this S max, if the width of extraction is this much only, say this blue color is the subcritical width, up to this much width the extraction has been carried out. So the maximum depression of the ground will be shown by the blue capital S. But as you go on increasing the width of the excavation, you reach to a point where the S max will be maximum, and beyond this, if you go on excavating, this basin will have a flat surface, and then it will go on extending. Let me check if that thing is there or not. Okay, so when the width of extraction at which you get maximum of the S max, maximum subsidence, where it has become maximum of all, that is known as the critical width. Okay, that is the red color one. So here you will get only one point which has maximum subsidence, and if you extend the extraction towards the right, this will go on getting horizontally, and then it picks up depending upon the width of on the angle xi. Okay, so here this basin will have a flat bottom for supercritical area. So this width, the width of extraction in which you get only one point of maximum subsidence, is known as the critical width. And when you get lot of points which has S max, then that is known as supercritical, and below this less than the value of the critical width is known as the subcritical width. Okay. Sir, why would we predict the subsidence when the subsidence has already occurred and the angle of draw is calculated only after the subsidence has occurred? See, this knowing the value of xi has to be done from the subsidence data. Okay. Now we need to predict subsidence because here you are seeing a greater magnitude. If I do mining in such a way that I extract little bit of mineral here, little bit of other place, a little bit of different place, so the extent of subsidence can be less or more depending upon how we are mining the underground. Now suppose you have a surface structure here and the mining company wants to extract the mineral. It approaches the regulatory body to say that please give me a permission, I want to extract this mineral. The regulatory body says that no, there is a surface structure above the your mining area, mineral area, we cannot allow you to mine. Then he approaches a consultant and then he asks the consultant, sir, please predict the subsidence and tell me whether there will be a subsidence, there will be too much subsidence which is going to break the building or to damage the structure above the surface. So there you need to know the you need to go for prediction of subsidence, and this xi, maybe the mining company would have done it on the other side where there was no surface feature. So from that data, the mining company has said that in my area I find that xi is having this much value. So this value of xi has been studied throughout the coalfield area. I'll come to that point, how much this value has been there. Okay, so for mostly coal mining area it varies from 30 to 35 degree. Okay, and that has been taken into account. Okay, is that clear, Abhishek? Okay. So for supercritical width, again the slope of extraction curves are different. So I hope with these graphs you are able to find out, know what is subcritical area of extraction, critical area of extraction, and the supercritical area of extraction. and these points is are denoted here by a small s and their length L. These are the subsidence observation points which people normally observe the subsidence on the mining area through surveying stations. These are the survey stations. Okay. In addition to this vertical movement, each point in the subsidence will also go horizontal movement known as displacement. Now see, suppose this was the point here. This point can shift to another point as the mining goes, progresses. So there is a change in the length as well as the direction of the point. And this, with this change in length and direction, one can very well find out the direction of the strain, how the strains are behaving. Okay. So primary parameters of interest with regard to subsidence are S max, maximum subsidence value, the maximum ground tilt, okay, and compressive, which are the places where tensile and compressive stresses are created in the ground, okay, and the minimum radius of ground curvature, the curvature of the ground that is being created. Okay, so let us, with this background, I will just show you the lecture material which was already uploaded onto your MIS. Okay, so I'll just quickly pass through this because most of the things have been discussed in the PPT. Okay, continuous subsidence, discontinuous subsidence, pillar collapse, this we have discussed, chimney subsidence we have discussed, sinkholes is discussed. Okay, the fundamentals we have discussed. Okay, and critical, subcritical, and all these things we have discussed. Okay, so whatever we discussed in this previous slide, that is how the strains are measured. So strains can also be plotted along the subsidence profile curve. Okay, so here what you see is blue one is the blue curve is for the subcritical width of extraction, and red curve and associated things are with the critical width of extraction. Okay, so we had discussed subsidence. So subsidence profile has not been drawn here, but another thing is that two more data have been plotted here. One is the strain curve. So this side up to the half of strain, that is the inflection point, the strains will be positive, and beyond the inflection point the strains will be negative. Okay, and then again it becomes symmetric after this value. So minus E max and plus E max, these are the two values which are of importance. See, for railway bridges and railway lines or bridges, they can tolerate a certain level of strain. If the strain goes beyond that limit, the bridge or the railway line will fail. So whether after mining, whether the strain is within the permissible limit or beyond the permissible limit, that needs to be known, and for this the value of strains are required to be done. Apart from this, this point before reaching the critical place, it was here. After the critical extraction, it has gone here. So there will be a displacement in the xyz coordinate. Okay, so that displacement curve can be plotted through these points. They also behave in a similar manner to the what we can say is the strain curve, but slightly beyond the inflection point. They are on the right hand side beyond the inflection point. Okay, sir, if you could explain the strain curve. Okay, strain is change in length per unit length. If the length increases more than the original length, the strain will be positive. Okay, so the positive strains are shown by plus here, and here there will be a compression. Okay, so beyond this point there will be a compression. So these are the compressive strains. That means here the length of two stations are decreasing as compared to its original length, and in this region it is increasing. So here tensile stresses will be created, and here this compression will be there. Okay, so on the edges of the you can say the subsidence profile, there will be more of tensile nature of cracks available, whereas at the bottom or center of the subsidence trough there will be not much of tensile fractures. Okay, some of the symbols that are normally used in subsidence engineering, these symbols are more or less standard, and they have been used by many people. So tilt or slope is defined by G. Okay, and that too, the slope of that line is expressed in per thousand. So if this point has moved to this point, from this point to this point, the slope will be delta S by delta X divided by 1000. So that is, in terms of subsidence, the slope is given always in terms of parts per thousand. Maximum slope is expressed by G. G max is the maximum possible slope that is occurring in the subsidence area. Okay, and G is the maximum slope in the subsidence area when the working is subcritical. So you see the difference. When it is subcritical, it is G, and when it is in the critical area, it is G max. And in supercritical area, G max will be always G max, because that is the maximum point you will be getting. So in supercritical area you get infinite number of points, whereas in critical area you get only one G max. That's the difference. Station levels are denoted by L. Plus minus E is denoted by the strain. Okay, maximum strain again in a what you say is the subcritical area will be given by capital E, and E max is for this critical area. Okay, and lengthening is plus and shortening is minus, given by minus. Similarly, for subsidence, at any point it is if you want to know the subsidence, it is given by small s. Capital S is for subcritical and S max is for critical, and S by 2 is the subsidence half, and it coincides with the transition point T, or the point of inflection, what we say. One important ratio people use in subsidence is the subsidence factor, which is denoted by A, that is denoted by the maximum subsidence in a critical area divided by the mining height. S max by M is known as the subsidence factor. This is important term which people have used in developing the graphical outputs. Okay. M is the mining thickness, and T is and the transition point or the point of inflection is denoted by T. Okay. See, in the a good work has been carried out in the Subsidence Engineers Handbook of UK. Okay, in UK coal mining area, lot of work was done in the area of subsidence, and the UK people, they published a Subsidence Engineers Handbook, and there they missed one thing, that is the non-effective width of working. Let us go back again to the graph. I'll tell you. I say that the subcritical thing here, if I extract a subcritical area, there will be a subsidence. Now say for example, if I extract only 1 meter of the width of the working, and if the height is 100 meters, is it going to create a subsidence? No way. That means there has to be a minimum width beyond which the subsidence will occur. Okay, so that width up to which there is no subsidence, or the subsidence is not observed on the surface, is known as the non-effective width. Okay, so apart from these three widths, subcritical width, critical width, supercritical width, we have now again come to one more term, that is the non-effective width. So that is also denoted by NEW sometimes. Okay, so coming back to that point. Okay, so this concept was initiated in India and Australia during 1989. Okay, regarding the non-effective width. Now the non-effective width to the depth ratio, depth of working, non-effective width of the working to the depth at which working is carried out is denoted by NEW, and for Indian conditions it is found that it varies from 0.2 to 0.8, and it depends upon the strata competence. So this is an important data that can be utilized for finding the non-effective width in Indian coal fields. And with this data, the critical width of extraction can be found out to be 3.5 times the non-effective width in single seam cases. Okay, whereas when multiple seams are extracted, it can be 6.5 to 7 times the non-effective width. Okay, the concept of non-effective width critical, again it's explained here. Okay, so you have an angle of draw, say theta, non-effective width. For this much width there is no subsidence. Subcritical width, if you extract up to this much width, there will be a subsidence S. S will be less than S max, and S max, here you will have only one point of S max when the width is critical, and you will get multiple S max points in this trough when the width of extraction exceeds the supercritical width. Okay. This curve was drawn by the Indian researchers just to show that the maximum subsidence value S will vary. It will not start from 0, it will start from here. So maximum subsidence is 0 up to the non-critical width, and then the maximum subsidence starts picking up when as the width of the excavation increases. Okay, so a similar kind of graph you will see in the NCB book. Okay, so we'll come to that, how these are predicted. Okay, so for subsidence prediction there are three techniques, basically the empirical technique, the influence function technique, and the theoretical modeling. Okay, empirical techniques are more popular because of the experience that are gained from large number of actual field measurements. People rely on these techniques because of this great thing, that is the experience. Okay, so and then the influence function methods are based on propositions and mathematical assumptions to a great degree, whereas theoretical models, they are based on analytical or mechanistic theory, rheology of the material, and reaction to changing mining scenario. Mostly it is done using numerical modeling. Okay, so one is the experience, empirical technique, another is because of the mathematical functions, use of mathematical functions, and the numerical modeling. We'll discuss each of them briefly. Okay, so empirical method, what happened? A graph was made by NCB, National Coal Board, in UK. Okay, this shows that subsidence by extraction height, S max by M. Okay, the subsidence factor which we discussed in the definitions is here. This is the subsidence factor, which is the ratio of maximum subsidence to the extraction height, and is to depth ratio. These two are plotted. You get a curve like this, and this curve has been plotted based upon the lot of data that were available in the United Kingdom coal fields. So when stowing is carried out, the width to depth ratio and the subsidence factor shows this thing. Say for example, you want how to use this graph. Say for example, you want to extract a 300 meter at a depth of 300 meters. So width to depth ratio becomes 1. Okay, and if the mining height is say 3 meter, okay, so your subsidence factor turns out to 0.4 for this much width of panel. Okay, that means 0.4 is maximum subsidence by 3. So your maximum subsidence will become 0.4 is equal to S max by 3. So S max become 0.4 into 3 charting about 1.2 meters, so you get a subsidence of 1.2 meter over that panel. Okay, this is how this curve has to be used when you are using stowing. Earlier people used to do stowing of the panel using strip packing also. Okay, so for that strip packing is nothing but it was basically small stone chips of say up to maximum size of 10-inch that were thrown into the groove of the excavated coal. Okay, so when the caving occurs, this coal will get compressed, and because of that compression this will also be more. Okay, so because so this graph also shows that the subsidence will be more. So similarly for your example of 300 meter width of panel, okay, at a depth of 300 meter your subsidence factor is 0.8. Up to 2.4 meter, 8 into 3 is 2.4 meter of maximum subsidence you will get in the same scenario if you resort from solid stowing to caving with. Okay, so you see you were getting 1.2 in one case of mining and another case of mining you are 2.4. That's the difference. A similar graph for depth of working according to the width of extraction versus the depth of working was plotted for those UK coalfields, and the subsidence to extraction ratio was S max M value, that is the subsidence factor was on the y-axis. So this can be used for in a similar way. Say for example here 300 meter at a depth of 300 meter, say for example 380 meters. Okay, your subsidence factor is 0.8. Here this is this made for the caving. When the mining is carried out with caving, that means you are not filling anything in the void, you are extracting the mineral and leaving it to fall in the groove. So in the case of caving, your this normogram can be used maximum subsidence in the basin. Now see, we had discussed about non-effective width. The major disadvantage of this NCB curve is that it is not taking into account the tip width. Its width is starting from 0. Okay, but then up to 100 of panel widths this can be found to be okay. Okay, so in the absence of data, people are using this value to predict the subsidence. Now these two graphs of the graphical technique are able to give you the value of the maximum subsidence, but it is not able to tell you what is the profile. So people have used lot of profile functions. Okay, I am not going into much through them. Okay, USSR function has shown. Okay, so S max you calculate from the graph, using the graph, and this then S value at a given distance can be calculated and plotted, and then you get the profile curve. Okay, similarly Polish functions have been used, Aryan profile functions have been used. These are all for your academic interest. Needhofer's profile function is there, Indian function is also given, but they separated it for two cases, one for subcritical widths and the critical widths. Okay, and the disadvantage of this Indian profile function is that it gives a broader subsidence trough than as observed in the field. Sampada, can you please repeat the usage of graphical method? Okay, okay. See, uh, when you do coal mining, you extract the coal. Now, when you extract the coal, you can pull in the gove to fall into the um, void, or else sometimes people use sandstone, okay, to fill the void in the gove. Now, why sandstoning is done? Sandstoning is done so that the void created by extraction is not left as it is, and it should be filled up so that no roof fall takes, there is no subsidence, right? So if you don't want subsidence, for stowing. But the problem with stowing is that you cannot ensure 100% of packing in the gove. At least 20 to 25 to 30% of void is left in the gove, and because of that void you get dense on the surface. Okay, say for example my width of my panel is say 300 meter, and I am working, for easy case I have used the case of 300 meter width panel, and I am working at a depth of 300 meter. So what will be the ratio of the width to depth? Width is 300 meter, depth is 300 meter, so this ratio be okay, right? So for a value of W by D ratio 1, I draw a vertical line onto this curve. Okay, and from this vertical line where this crosses this curve, I draw a horizontal line towards the y-axis, and I get a value of 0.4. That means my subsidence factor is equal to 0.4, right? So 0.4 is equal to subsidence divided by extraction height. Okay, say for example my extraction height is 3 meter seam thickness, height of extraction is 3 meter, so S by 3 will be equal to 0.4, right? So S will be equal to 4.4 into 3, which is equal to 1.2. That means with this graph I am able to find out what is the subsidence when, in the case when the width of my panel is 300 meter and I am working at a depth of 300 meter. So any width of panel at any depth will fall into these ratios, 0.1 to 0.2. And here what you see, one thing is, beyond this width to depth ratio of 1.4, saturating, this means that as the width increases I am getting a supercritical subsidence profile. That's why this curve is saturating. So this is how you use this graph number 1. And if you don't want to do stowing or filling, then you can leave the material in the gove to fall, and that is known as the caving method of mining. So for different depths you have different curves. Say for example 760 meter you have this curve, 610 meter you have this curve, 610 meter of working. Okay, now if you know the width of the extraction, say for example 300, and again let me say take the previous example of 300 meter depth of working. So I draw a vertical line from here up to 305 meter of line. So I am getting 0.9. My subsidence factor is 0.9. So 0.9 is equal to S by 3. Extraction height I'm assuming it as 3 meter. So 0.9 into 3 is 2.7. So for this case, with caving, my maximum subsurface will be around 2.7 meters. This is how you used to calculate it. I hope you will be able to understand this concept. Sampada, now is it clear? Anuradha is telling, sir, I am unable to see the document. Have started on another computer, is going on, and I'm able to see the document. Probably your internet speed may be slow, or else you can try with 144 pixel or a lower resolution, so the streaming is faster and you get with a different setting of the pixels. Probably you will get it. Okay, so we move to the other thing. Okay, Sampada, it's clear for her. So these profile functions methods have been used. Some people used hyperbolic functions, trigonometric functions. Lot of mathematical functions have been used. I have given only 6 or 7 of them. Okay, another method is the use of inference. Okay, this method is still being used by the consultants in our country to predict the subsidence, and using this influence method you can subsidence at any point in the subsidence profile. Please pay attention on this, and I will show you one example also. Okay, with that you will be able to understand how the things are calculated. Okay, this influence method is basically described by a function kz, which is a function of, okay, and it uses the fundamental concept of extraction of an infinitesimal area dA causing infinitesimals at the surface. See, the algorithm is very abstract, mathematical. Okay, so you have to pay a little bit of it, and in this online cases it becomes very difficult to see who is understanding or not. But anyway, put the things in your chat. Okay, so it relies on the cause of infinitesimal subsidence based on extraction of infinitesimal area dA. Say for example this point P, you want to see the subsidence. What you do is, this point P, what is the influence of the extraction of this element, element 2, element 3, element 5, element 6 and element 7 at this point, that can be found out by finding the total subsidence. So the function, influence function kz, is basically dependent on the element dA. Suppose one element dA I extract with this, so function associated with this is something like a probability distribution curve, okay, which has a maximum value at the center of element and it goes on reducing. So when I apply this function and I integrate it throughout, I get a curve for 1. Okay, so for 1, if I extract this element 1, the subsidence will be, profile will be something like this, given by curve 1. When I extract element 2, I get a subsidence curve like this too, using this influence function. Okay, so all these 7 elements, when they are, I got 7 curves. When I add all at this point, if I add the subsidence value of this, I get a point here. Similarly, I go on adding the subsidence value of all the curves, and at this maximum point, subsidence value of all these things will be 7 times, because 7 curves are there, so 7 times of this, so I get a maximum curve. So this is the overall curve I am getting because of the extra all these elements. Okay, this will be more clear as I expose you to numerical example. Okay, so the subsidence is nothing but, to do it for the complete area, you have to integrate along that area using a infinitesimal and the influence function, so you get a maximum subsidence. Okay, when you are using the xyz coordinates, and when you use the polar coordinates, the function kr r dr theta d theta dr can be used. This way you can find out. Okay, let me say one more thing. Say for example, on the same little simplification of the above concept, here it is shown like this. Okay, say for example, I extract this much width, a width which is smaller than this area. Okay, and at the center of this point P, I need to know the subsidence. What I do is, I am extracting one annular ring, I get an influence function, then I extract the second annular ring, influence function, and when I add all these things at this point P, the complete subsidence can be found. Okay, some of the influence functions that have been used are these functions. These two functions, Kane-Hosts, he gave another function, Ball, he gave another, Bayer, he gave another function. Okay, from different country people have given different formulation. In Indian country, the Severage influence function, that kz function is given by 0.3 r square into 1 plus cos theta pi r square by r. Okay, so this concept, how it is utilized, I'll show you numerical example that will be clear to you more. Okay, let me open the numerical example. Okay, Anuradha is able to see the okay. Okay, so we try to understand the concept of influence function in example. Okay, this was there in one of the exams, last year exams for BTech. Okay, it says that a coal seam of 3.5 meter thickness is worked at a depth of 357 meter in conjunction with caving of the overlying strata. The subsidence history of the mine reveals that the angle of draw is 35 degree. See, the subsidence history of the mine reveals that the angle of draw is 35 degree. You need to know it from the subsidence history. Okay, and the subsidence factor of the mining area is 0.81. Right, in half of this NCB has not been used. Rather, directly the subsidence factor has been shown to be 0.81. Now, the question is, the radius of, determine the following: the radius of the influence circle, the maximum possible subsidence, The plan is given in the figure attached with the scale of 1 in 100. Subsidence values at any point can be determined using influence function method. The influence function is given by the equation this. Influence function is basically the Seurès influence function. Okay, the first step is you have to draw the radius of the influence circle on a tracing paper, right? Something like this. Okay, and then you have to divide it into 5 concentric rings, equal rings, 5 equal concentric rings, and there should be 6 sectors. Okay, so we need to find the weighing factor for each of the concentric rings. Okay, and then we have to find out the maximum subsidence. So how it is to be done? So this is the plan view of the panel is being extracted by board and pillar mining. Okay, you need to know beyond the point E what is the subsidence, at point F what is the subsidence, and just above the panel what is the subsidence. So all these places you will have different values of subsidence. If you know the algorithm to calculate the subsidence at one point, you have to calculate at all the points, and if you calculate at all the points, you can very well draw the contours of the subsidence basin. Okay. So this was just for exam purpose which was given, and most of the students did it. So with the given data of the question, your mining height is 3.5 meter, depth of working is 357 meter, alpha is 3, and subsidence factor is 0.81. So S max will be A times M, which is 2.83. That means the maximum subsidence which you will get is 2.83 meters in the basin. That is one data that has been taken out. Now you need to draw the radius of the influence circle. This radius of the influence circle is nothing but h times tan alpha. Okay, which turns out to be 250 meters, because h is 357 meters, influence angle of draw is 35 degrees, so this. Okay, and you have to use this kz. Now in this concentric ring, say for example, are you able to see these concentric rings? Okay, this way you have to draw, and the radius has to be scaled to 250 meters. Okay, then kz d alpha r dr, and this theta will vary from 0 to 2 pi. Radius will for the first influence circle, radius will be 0 to 50 meters, because your complete circle is 250 meters. I have divided into 5 equal circular area. So if I extract the central annulus, the influence weight will be integrated over 0 to 2 pi, and r will be integrated from 0 to 50 meters. Okay, and I use the function kz. These constants will be taken out, r into 1 plus cos 2 pi r, this will be there. Okay, and then you can integrate it. Okay, finally manually, using manual integrations, you can find out the for the first ri minus 1 is 0 and ri is 50. Okay, that turns out to be 0.1280. Calculator, if your calculator is not that smart, you have to calculate it, or else now those smart calculators which you have used, some of you have used in your class, you can directly find integral using this function, and for the first ring you get 0.1280. so if I extract the first ring, the weighing factor is 0.12. For the second ring, similarly, the limit 50 to 100 meters. That turns out to be 31.27. Okay, the same integral, you just need to change the limits. Okay, and third is 0.32, fourth is similar way, you get 0.1, fifth one you get 0.0369. When you add all these 5 weightage, 1, 2, 3, 4 and 5, all these 5 weightage, you can cross check that this integral it is there in the theory. Okay, all this sum will be unity. So this way you can also cross check that this has to be unity. Okay, and then what is, when you draw these circles, so for the ring 1 your weightage is 0.128, ring 2 you go on making a table like this for the weights. Okay, now the second work is, on this plan you superimpose this circle. Okay, say for example you are placing the center of this circle at over point A. Okay, the center of the circle sided with the point A. Let me see. You have to coincide the like this. Okay, and then in the first ring you have to count how of them are falling inside the extraction area. So obviously in the for point A, all sectors are falling in the extraction area, and similarly for the second ring, again all the 16 are falling in the extraction area. Here in the third ring 3 are not falling in the extraction area, they are outside the extraction area. 18 are inside extraction area, fourth ring 12 are inside the extraction area, 11 are there in the extraction area. So point A, what we do is we multiply this weighing factor into the small sectors which are within the extraction area. Okay, so this is 0.12 into 16, 0.16, okay, and so on, last up to 0.30369 into 11. Okay, and then we divide it by 16 and multiply with the S max. That means 16 of them have contributed to the 16 elements of first having a weight of this much has contributed, 16 of this much weight has contributed towards the maximum subsidence. So that would be 2.51 meter. Okay, similarly a subsidence at point B, C, D, E and F can be calculated. Okay, so this is how this is the algorithm how the subsidence is calculated. Anuradha is asking, sir, could we do this numerical example session in next class, as because I am facing internet issues. I am posting these lectures on the uh, Google Class also. It will be deleted after your exams are over. Okay, so those facing internet issues can access this lecture later on also. Okay, so this is the way this related, and one good example could be, application of this could be, say for example, okay, suppose a railway line is crossing through the point F from here. Okay, now this point F side the mining lease area, but when the complete panel is extracted, whether the subsidence is enough to create damage to the railway line, how do we know? That can be found out using this influence function method. So this is the application, and once you exercise it, you will be able to do it. Okay, in the regular classes I used to ask the students to do it in the class itself, so they were quite confident to do it, but in online classes I am not confident how many of you will be able to get it. But anyway, if any issues are there, you are always welcome to discuss me through the mail. I'll be able to guide you. Okay, so this is how the influence function method is used to calculate this. Okay, now coming back to our lecture. Okay, so that algorithm was for finding out the maximum subsidence. How to find out. The same algorithm has been applied for finding out the displacement. Okay, so for this what they do is they take one element, find the subsidence, that is the vertical displacement because of this extraction of this only one element in the annular ring. Okay, and it is in this algorithm it is assumed that because of this thing there will be a displacement towards the center. Okay, and that will be dictated by angle beta. Okay, and in the plane it will be tan j by dvz. Dvz is the vertical displacement, and dvz is calculated subsidence factor or the weight of that using that integral method into S max. You find the vertical displacement, and tan j will give you the xy displacement, and if you use the angle beta, so in the xy plane in which direction they are moving, that can be calculated. Okay, so using a computerized method, all these elements and all the vector displacements, they are calculated and summed over to find out at this point P is the direction of the displacement. This is how the displacement is found out. Okay, doing hectic tasks, it has to be computerized. Okay, a computerized solution is available. Okay, theoretical methods rely on finite element, distinct element method. Okay, but not much of confidence has been built up with these models. Rather, this influence function gives more confidence in of the subsidence. Okay, so people are working extracting the mineral partially below the underground, and the method of extraction of mineral partially is known as partial extraction method. Okay, so there are six methods that utilize the non-effective area. Okay, non-effective method of extraction: the chessboard method, Goff pillar method, pillar thinning and heightening, splitting of pillars and stowing, splitting of pillars and side bolting. Okay, so in this, the width of extraction is kept extract L. If L is the width of my extraction, I have to decide that L should be always less than effective width of working. Okay, the moment it is less than non-effective width of working, there will be no subsidence. Pillars I am leaving in between the panel, that should have at least a factor of safety 0. Okay, so if I start leaving a small, if I take my mineral in gaps of L, which is less than the non-effective width of working, and if I leave the pillars which have factor of safety more than 2, this is not going to create a subsidence over the surface. Okay, so these are the methods of work. You can utilize the chessboard pattern of extraction of the pillars. Leave one pillar in the row, leave one in the other column, and you get a chessboard pattern, and the effective width of the working can be L. Okay, that way the non-effective width of working is satisfied, the subsidence is prevented. Okay, now in this case you need to also ensure that the factor of safety of all these pillars should be more than 2. Okay, for that is not using a tributary area method, a different approach has to be used, and you get the load on the pillar formula, and then you find out the factor of safety using the strength criteria. Okay, Goff pillar method, in Goff you can leave 2 pillars such that the L is a non-effective width of working. Okay, 4 pillars can also be kept, but throughout this thing L has to be less than NEW. Here also it has to be NEW, here also it has to be NEW, all 4 sides it has to be less than NEW. Okay, pillar thinning and heightening can be done. Sidewise pillars can be extracted so that there is no so that the subsidence doesn't approach the surface. Okay, pillar splitting and stowing can be practiced. Okay, a pillar can be split into 4 parts, stowed. Okay, when stowing is not possible, then pillars can be left and then it can be stitched to get greater safety, factor of safety. Okay, in some panels what happens is that you always do not a clear cut rectangular shape. When in a panel, when a diagonal line is extracted, the effective, if this is the L, the effective width has to be less than L. Okay, so that factor has to be utilized. Okay, so this is a step diagonal line, this is step diagonal line with half step that has been followed, or you are leaving L like this. Okay, so in such cases the effective equivalent width will be, for this step diagonal system it will be 0.54, steep diagonal 0.57, Okay, 0.7 for this pattern it is 0.6, chessboard pattern 0.67. Okay, this will be the effective width that can be utilized in the formulation of the uh, yeah, subsidence prediction strategy. Okay, so this completes the part. If you have any doubts, if you have some more doubts, you can ask. Okay. Okay, if there are no doubts, I'll be closing here.